These typically have significantly lower bypass ratio engines and are found in military jets. If it's not turbojet, it'll have a turbofan engine of this style, where you're trying to get the performance of a turbojet, in terms of, a high specific thrust, but still pick up some fuel economy through the idea of it being a turbofan engine. With this type of turbofan engine, once there's compression of the cold air, it comes down here and is mixed with the hot air before both streams as a mixed entity are expanded in the single nozzle, okay? Does that make sense? And what I'm showing on this drawing, unlike the one that you all are going to be doing, is on the fan of the low pressure compressor, I have more stages of compression across the fan root than the fan itself in the cold part, okay? And that is common, especially in this style of turbofan engine, so I would specify an overall pressure ratio, and then I'd specify a root pressure ratio and a fan pressure ratio, and you can handle that, okay, in terms of computing what the specific work is. This is an analysis that I had. This was actually the midterm exam when I used to teach propulsion 17 years ago. And you can specify isentropic efficiencies independently for the root and the actual fan part. So that's what I mean by the military style turbofan engine, meaning it would be a more high performance thing with respect to the thrust, specific thrust that it produces. Anyway, back to the type that we're going to focus on here in your all's assignments. Anybody wants to, to work a problem with this thing? I have a complete problem you can do with it or study. We're looking at course notes, and we introduced this system last time. And now we're going to do a sample calculation. Not that one. I'm going to close that one out. Okay, we defined all these terms in terms of, flight mass, flow rate, considered bypass ratio, fuel air ratio defined with respect to the hot system, the hot nozzle or hot stream, the overall fuel air ratio, how based on conservation of mass and definition of bypass ratio you can compute these various mass flow rate fractions. And then this is how we're going to compute specific thrust right here. We're going to compute a momentum and pressure thrust for the hot nozzle and a momentum and a pressure thrust for the cold nozzle. And then our TSFC is defined the same way, but it's going to involve the use of an F overall, which is the actual fuel rate compared to divided by the total mass flow rate of the air. Now, the performance of this system is basically controlled by 6 parameters. 2 of them are flight parameters. So basically, flight conditions. MA and altitude. And we're going to do these the same as the turbojet. Our calculations are going to specify our flight conditions the same as the turbojet. Okay, and then your engine design your basic engine design parameters that control the performance of the system from an engine design standpoint are turbine inlet temperature, which is T04, and then overall pressure ratio, which according to the numbering system that I gave for that, for the turbojet and for this turbofan engine, that would be P03 over P01. So this, this is what it is for the turbojet. For the turbofan, we've got to add two more. Okay, one is bypass ratio, and that's defined to be the mass flow rate of the cold air over the mass flow rate of the hot air. That's the bypass ratio. And then in addition, we would do fan pressure ratio, which is the low pressure ratio. It's the pressure ratio of the compressor, low pressure. Okay, and it is P0, this will be P02 over P03. And then, by the way, pressure ratio of the compressor, high pressure, will just be, as you would expect, overall pressure ratio divided by pressure ratio across the compressor, LP. Okay, so in the turbo jet engine, these two things are principal design variables as they are in the turbofan. And of course, you have to pick a fan pressure ratio, but it is not critical what you pick, really, at least from the analysis in this standpoint. So once you pick this, okay, then the high pressure ratio across the high pressure ratio is then locked in. But these four right here control the performance of this system in a primary way. So in this system, the fan pressure ratio is very, very important. We're going to pick, we're going to do these the same. For this calculation, we're going to take this to be 1200 and this to be 9, like we did. Okay, what I'm trying to do is make everything in this initial calculation the same as we did with turbojet, so we can sort of compare and see what we got as a consequence. Okay? I'm going to take a bypass ratio of 2. Okay? And that's just brand new. Well, actually, the bypass ratio for the turbojet is in effect 0, right? That's what you get for turbojet. There's no bypass. And we're going to take this to be 3. And the reason for that is because the low pressure ratio was set to be equal to the high pressure ratio, or the square root of the overall. Okay, so I'm taking this to be 3 just so it will, our first calculation can compare in the best way to the turbojet. Does that make sense? Now the combination of these is very, very important. Okay, they tend to represent how much energy is being, they tend to represent how much energy is being taken out of the hot stream and put into the cold. Okay, if you look at the system, okay, everything done by this low pressure compressor comes from work done by the low pressure turbine. And the low pressure turbine derives its power from the hot stream. So this thing, the energy from the hot stream is basically being put into the cold stream. Okay, so if you have a high bypass ratio, you have a lot of mass in the cold stream that you're trying to compress, and when the pressure ratio across here is high, that combination can be overwhelming, okay, to the system. And the real life system, what we're going to see is the bypass ratio goes up. As this thing goes up, a good design means that this thing will go down for a good design. And this combination of bypass ratio and fan pressure ratio does not, it's a feasible design theoretically, but it's not what I'd call a good design. Okay, but I want to do the calculation with these parameters first, okay? So, isentropic efficiencies, where applicable, are going to be the same as in the turbojet. So I'm trying to make as much of a one-to-one comparison as I can. So, if we proceed with the calculations, okay, starting at the inflow and stepping at the first device is the inlet, right? And the inflow conditions are the same as turbojet, and with the same isentropic efficiency, the outflow from the inlet, which is the inflow to the fan, there's no change. Gives the same result, okay? By the way, you're going to be surprised what minor modifications you have to make to your turbojet program to make the turbojet program do your turbofan calculations and thus do homework 6. Okay? Analysis of the low pressure compressor, because it has the same pressure ratio across it, 3 as the turbojet had, and because the isentropic efficiencies are the same, I'm going to get the same stagnation conditions leaving the fan. And remember, on the fan, we're saying that those conditions are the same at the root and out at the tip. So basically, we have computed conditions here and here. We've computed the conditions that are going to drive the cold nozzle and the conditions that are going to inflow to the high pressure compressor, okay? Now, here's where you're going to get your first change. This is very, very, very key, okay? The specific work of the low pressure compressor, okay, based on the mass flow rate of the total air, would be this. Okay, and that's exactly what you computed for turbojet. Okay, but we want to compute the specific work based on the mass flow rate just going through the hot part of the engine, because that's the mass flow rate that we're going to be working with in the hot part of the engine. Okay, so we don't want a specific work based on scaling this thing by m dot air. That's the total air. We want it based on m dot hot. And we're going to call this the specific work of the low pressure compressor star. And it's defined as the power input to the compressor divided by m dot hot. Okay? And this thing right here algebraically can be calculated this way. We can multiply, to calculate this, we can get the specific work defined as we did before, times the ratio m dot air over m dot hot. Okay, and m dot air is m dot hot plus m dot cold, and we've seen that this is just bypass ratio plus 1. Okay, so the quantity that we want, the specific work of the compressor low pressure, that is the fan, star, that is the value scaled by m dot hot, uses the same calculation that we had before, but you multiply it times b plus 1. Okay, and our b is 2. So the result that you're going to calculate is actually 3 times as great. It's 3 times as big as this number right here. Okay? And what you basically got is basically, it's a power based on, in effect, 1/3 as much air. You know, it's just you know, if you look at m dot air as it's saying, that it's I don't know if that's correct. Okay, but it you know, this right here, this m dot hot is 1/3 of the total airflow rate, right? Where and what you did in the turbojet was the specific work that you were doing was the full m dot air was equal to m dot hot. Okay. here you're only doing a fraction of m dot air. So anyway, this, if you were to take your computer program for turbojet to make it do turbofan, one addition right here. That, so far. It's not going to be much. Okay? So, and then from then on, if you want to do turbojet, you just specify B equals 0, right? This is not a big deal. This is going to be one of the simplest assignments once you have turbojet going. So if I continue on, okay, if I continue on with the same isentropic efficiencies and the same inflow conditions to the high pressure turbine, I actually calculate the same outflow stagnation conditions. And my specific work based on m dot hot, okay, this is the full mass flow rate. Okay, going through this system is m dot hot. I'm operating now totally on the hot stream. So my specific work based on m dot hot uses the same formula as turbojet, and I'll compute the same specific work based on m dot hot. Okay. Now when I go into the combustion chamber, all I know, the only thing that's going to control what my fuel-air ratio based on m dot hot, okay, will be my inflow temperature, which is the temperature of the reactants, the outflow temperature, which is the temperature of the products, which is T04, and then what fuel am I doing? Okay, and the fact that we're going to specify excess air always. So I'm going to compute the same F ideal. Remember, this is F is m dot fuel over m dot hot. You know, the air is m dot hot, not m dot air, which is the total. Okay? So my F ideal, this is what your computer program, homework 3 part 1, when applied to this, should give you. Same as turbojet. Then you adjust it with your burner efficiency. So this is what you're really doing. Burner efficiency of 0.98, same, I'm using the same burner efficiency. Okay? And then P04 is adjusted with this burner efficiency in terms of a stagnation pressure loss factor of 4% of the deliveries lost. So this is all same as turbojet. Same numbers, okay? Everything you're calculating is the same. The only number that you'll have that you're storing but haven't used yet, you'll have this number in the computer based on multiplying this times B plus 1. You'll have this number rather than that number. Okay? It's the only thing that's changed, but it's subtle. Because when you go into the high pressure turbine, the same isentropic efficiency, the same specific work, the same inflow conditions, you get the same outflow conditions. This is exactly the same as turbojet. And the high pressure turbine is driving the high pressure compressor, all based on m dot hot, right? Okay. Here's where you get a difference. When you move into the low pressure compressor, got the same inflow conditions coming into the low pressure compressor, but based on m dot hot, which it's operating on, and from which it generates its power. Okay? It's basically going to have to, it's going to see a much greater specific work based on this m dot hot than it saw in the turbojet. So it's going to, there's a lot more energy is going to be taken out of the m dot hot stream. So we're going to expect a much lower stagnation temperature and a much lower stagnation pressure. So here's where the change comes. Okay? So the derivation of this, it's not a lot, okay? It's, the power of the low pressure spool, what it has to do, this is a positive number, is equal to the power of the low pressure compressor. And I put a minus here so that I have positive divided by positive. Positive equal to positive. And this is a negative quantity. And this is a mechanical efficiency that increases the amount of work, okay, that the actual low pressure turbine has to do. Okay, so this power input to the low pressure compressor can be expressed as m dot air, the total air, times the specific work of the low pressure compressor, that is based on an m dot air perspective, or it can be equal to m dot hot times the specific work of the low pressure compressor based on an m dot hot perspective, which is the way we did it. Okay? And then we say, okay, the power input to this turbine is equal to the mass flow rate exiting the hot nozzle. Okay. Power generated by this low pressure turbine. Okay, this is power generated by the low pressure turbine. It's going to be the mass flow rate exiting the hot nozzle times CP0 for the gases. So it's operating on products of combustion now, not air, times the stagnation temperature change, which will be T05 minus T06. This is the first law. Okay, and what is this? The mass flow rate exiting the hot nozzle is equal to the mass flow rate, okay, of the hot air plus the mass flow rate of the fuel. Okay? And the mass flow rate of the fuel is equal to the mass flow rate hot times the mass flow rate of the fuel over m dot hot. Okay, equal to m dot hot times F. So this thing basically says the mass flow rate exiting hot is equal to m dot hot times 1 plus F, where this F is based on the fuel-air ratio of the combustion chamber. You all see that? Okay. So my mass flow rate exiting the hot nozzle is the airflow of the hot stream times 1 plus F. Okay, now what did I say this thing was for the compressor? It's m dot hot m dot hot times the specific work input to the low pressure compressor star with a minus here divided by this mechanical efficiency. So my m dot hot cancels, but I do need the specific work of the compressor, low pressure compressor star. The power needs to be scaled by m dot hot. So I jack this equation around and say T06, my outflow stagnation temperature, is equal to my inflow stagnation temperature. And then I need to have my specific work here from the low pressure compressor star. This is the one you store, just like you did. Whatever you store, just like in the turbojet calculation, whatever you store in your low pressure compressor calculation. That's what you need to put here as a negative number. Okay, store it as the negative number as it is. And then you need these things as well, and you will have calculated F, and I told you how to calculate CP0 for the gases based on R for the gases equal to R for the air, and gamma G equal to 1.43s, okay? So, based on all this information needed in here, okay, T06 turns out to be this stagnation temperature. This is what's going to drive the hot nozzle compared to the turbojet of this number right here. So there's the big change. Finally, we see a change. Our T06 is different, driving the hot nozzle. But there's just been one little change to the computer program. You multiplied something times B plus 1. That's all you have to do to get here. For your stagnation pressure, assuming the same isentropic efficiency of the low pressure turbine, it's the same formula. But you do now have a different stagnation temperature, T06. Okay? So P06 is only this value right here compared to P06 of this before. So stagnation temperature and pressure are much lower to drive this hot nozzle as expected. Are we okay with the pressure this low? Is there a limit on how low that can be? What would be the limit? Back pressure, right? If it goes below the back pressure, then what you're going to have is your nozzles, theoretically, it's going to have a reverse flow going into it. Okay? Remember, you want stagnation pressure and its relationship to the back pressure. Stagnation pressure driving the nozzle has to be higher than the back pressure, right? I want to warn you that when you program up your turbofan engine, okay, for your hot nozzle calculation, and that will be just your nozzle calculation coming from your turbojet program, you should put a check at this point that you don't need previously. Examine the stagnation pressure coming in compared to the back pressure. And if that inflow stagnation pressure is less than the back pressure, you should just basically write yourself a comment on physical design, stop. Okay? You don't need to do it. Okay? If you proceed with the calculations, your computer program will blow up. Okay, the consequences of it will be, if you track through the computational tree, what you'll end up doing is you'll get a negative temperature at the exit of the nozzle, and then you'll go to compute the local speed of sound at the exit based on square root of gamma RT, and you'll try to take the square root of that negative number and, boom, you're done. Okay, so if you don't want that error, you can just avoid it and tell yourself what's going on and stop the program in the normal manner, okay? So what's going to cause low stagnation pressure and temperature for that matter, driving the hot nozzle, is a combination of this that takes an excessive amount of energy out of the hot nozzle. Does that make sense? And you can see our calculations can proceed, but this is not a good combination. It's too much energy. Okay, taken from the hot stream. So this is a comparison of what we've got driving the nozzle so far with the turbofan with these bypass and fan pressure ratio specifications compared to turbojet. The hot nozzle calculations can proceed, okay? And so you'll go into your your hot nozzle, which is just as far as you know, is the same nozzle calculation the turbojet nozzle would do. And you'll have an isentropic efficiency, you'll have these inflow stagnation conditions, and your goal is to compute the static pressure at the exit of a hot nozzle, the density at the exit of a hot nozzle, and the flow speed at the exit of a hot nozzle. And there'll be a momentum and a pressure thrust for both of those. I mean, for the hot nozzle calculation. And the first thing you do is you set up your choke test and determine if it's choked or not. And depending on whether it's choked or not, these three quantities you need to calculate have a different computational tree, okay? And you'll find in this particular case that our hot nozzle is unchoked, okay? We don't have much stagnation pressure driving it, okay? So the choke test requires you to calculate this choke parameter based on the gamma and the isentropic efficiency that is applicable. And it's important that you calculate this because in the cold nozzle, you're going to do the same thing. In the cold nozzle, you're going to have an isentropic efficiency of the nozzle cold, and I'm going to make that the same as the hot, but you're going to be using a different gamma for the air. Okay, so you create your choke test parameter, and it's this value, same as turbojet for reasons explained. And you compare what your back pressure is compared to your inflow stagnation pressure. Okay, so here's what you create, and here, based on your back pressure and inflow conditions, and this is your choke test, and we have an unchoked nozzle. So that means our exit pressure of the hot nozzle is equal to back pressure, and we're not going to get any pressure thrust out of this nozzle, but we will get a momentum thrust. So you follow the computational tree for an unchoked nozzle here. You compute the pressure at the exit of the hot nozzle, the temperature at the exit of the hot nozzle, so that with that pressure, okay, and temperature, you can compute the density at the exit of the hot nozzle. And now you need the flow speed at the exit of the hot nozzle, which is going to be less than 1, okay? And here's the computational tree that I showed you, based on stuff you know, stagnation temperature driving it, and the exit temperature. You can get the Mach number at the exit of a hot nozzle, and then the flow speed at the exit of a hot nozzle, okay? So you need this for your momentum. I mean, you need this for to calculate specific thrust, okay? And if you're doing a turbojet calculation, you'd be done. But you've got to consider what the cold nozzle is doing. So you're going to have to, in addition to just simply adding B+1 in the code, then you've got to go back and do another nozzle calculation, because your thrust is going to require you, your specific thrust. This is all the hot nozzle thrust, but here's the cold nozzle thrust, and you need pressure at the exit, density at the exit, and flow speed at the exit of the cold nozzle. Okay, so you need those things to compute FS. All right? So all you have to do is add a cold nozzle calculation that works exactly like the hot nozzle calculation. Okay, so let's look at the cold nozzle calculations. You compute your choke test based on the given nozzle efficiency, which could be different from the hot. It's not here. And the gamma for the nozzle, which is different. It's 1.4. So here's your choke test criterion. Remember, if the isentropic efficiency is 1 with gamma air equal to 1.4, this is 0.52828. But this is what the choke test is based on the adjusting for the isentropic efficiency. You form the back pressure ratio over the inflow pressure, which is P02. Okay, it's the pressure on the other side of the low pressure compressor. And you get this and you make the comparison, and the cold nozzle is choked. So you go through the cold nozzle computational path. Okay, you know that the exit Mach number is 1, the exit pressure is P star, blah, blah, blah. Here are the quantities you need. The pressure at the exit, the density at the exit, and the flow speed at the exit. And then putting all this together, okay, putting all this together, there's everything you have at your disposal based on calculations and given conditions, okay? Your FS calculates as your specific thrust from the hot nozzle and the specific thrust from the cold nozzle. Very low from the hot nozzle, okay? Much higher from the cold. Good design will generally have a better balance on that, okay? So FS is this number, okay? And what does it represent? It's the thrust for every, it's the thrust produced for every unit of mass air ingested by the system. And this number is expected to go way down, okay, with a turbofan engine. The higher the bypass ratio, the more it goes down. And that's a bad thing, but it's compensated for in these systems by processing a lot of air, okay? See, this is what you're calculating, okay? But what is it? It's your actual thrust divided by m dot air. So if you calculate, you know, if you have a lot of m dot air, you multiply it by this to get the thrust you need. We talked about that. Now your fuel consumption, your scaled fuel consumption, your actual fuel consumption per unit of thrust produced. Okay, you can't calculate based on information we have either of these numbers in the ratio, but this mathematically is equal to this ratio, both of which we can calculate. Notice that it's F over all. You know, this is this is F over all. F over all. You know, F. Okay, is m dot fuel over m dot hot, whereas F over all is equal to m dot fuel divided by the total air taken in. Okay, and that turns out to be F times bypass, F over all turns out to be F divided by, which you've calculated, divided by B plus 1. Okay? And this shows the math behind it. It's this ratio stuff. So, TSFC is your F based on your combustion chamber calculations, divided by FS, divided by bypass ratio plus 1. So this is a simple little adjustment you can put in your program, and this is what you get. So these numbers, when you've done your program right, will be what you should get. This is like your benchmark. This is a cookbook gig for doing this right, okay? With test numbers, you know, that you can verify every stage. Now let's look at some things in terms of what, you know, what's going on here. Here's our comparison. Okay. Here's our comparison. Okay. I want to get some of these over here because I might want to comment on some of this. What I have there is what the turbojet was for FS and TSFC, and what the turbofan gave. okay? So we lost a lot of specific thrust, 63% of our specific thrust, okay? And our TSFC only dropped by 8%. It's not trivial in this business, but considering the penalty we paid in specific thrust, I don't think it's impressive, okay? So what I'm going to do now is try a low bypass ratio with the same fan pressure ratio. And the reason for that is just to, I want to keep the fan pressure ratio the same for now. Okay, but I do know that we took a lot of energy out of the hot stream, so if we lower one of these or both, we won't take as much energy out, and maybe we'll get a better design. So if I go back and redo the calculations, I don't need to do the turbojet calculations, okay? This is what the results are, and I actually think this is a better looking design, okay? Typically, as you go up in bypass ratio, you know, you see these trends. The design was so bad that I think you actually see an improvement with decreasing bypass ratio here, okay? Now what we're going to do is we're going to keep overall pressure ratio and turbine inlet temperature fixed. We're not going to change that in any of our comparisons. But we're going to go back to a bypass ratio. We're going to go back to a bypass ratio of 2, which was our first bypass ratio attempt. But now we are going to change the fan pressure ratio, and we're going to try to take less energy out of the hot stream, not by lowering the bypass ratio, but lowering the fan pressure ratio. Lowering the fan pressure ratio. Okay. We're going to lower it from 3 down to 2. Okay. And to me, to make the comparison fair, I thought it was important to redo the turbojet calculation in this case, because the turbojet is operating on a low pressure ratio of 3, right? But now the turbofan is operating on a low pressure ratio of 2. So I went back, and instead of making the pressure ratio across both spools the same, 3, in the turbojet, I made them basically 2 and 4.5. Does that make sense? Because the overall is kept at 9. Everybody got that? So I'm lowering the fan pressure ratio from 3 for this turbofan calculation compared to the first calculation. And I'm redoing my turbojet calculation because I want to compare them on as even a footing as possible. That makes sense? Okay. So with that calculation, this is the turbojet numbers now. And you'll see it's almost indistinguishable. See that 5.36, 0.6, 0.112987. What was it? 5.358, 11298. You see what I mean? Almost no change, as I promised. Remember I told you in that system, the distribution of the pressure rise across the spools does not impact the turbojet much. That's why we don't make a big deal out of it, okay? The impact here is great. Okay? So, now I go back and do the turbofan calculation with this, and here's the comparison. Okay? Bypass ratio is 2, but now the fan pressure ratio is 2. We lost 68% of our specific thrust. You remember the thrust can be obtained. But now we're down 19% in our TSFC. It's the best design so far, right? Wouldn't you all agree with that? Okay. Let's lower the fan pressure ratio even more. Same bypass ratio. Okay? No, take that back. The way these modern high bypass ratio engines work, they run really high bypass ratios. Okay? And then the fan pressure ratios are just really tiny. It just makes the fan like basically a propeller. Okay? They'll have like one stage of compression, and the pressure ratio across it will be like 1.2 or something like that. You know, 1.4. Okay? So I'm going to go, this would characterize a high bypass ratio engine to be a bypass ratio of 5. So I'm going to take this thing down to 1.4. I'm going to have to recalculate the turbo jet, right, to have an overall of 9, but the first stage 1.4. And what will the second spool be? 9 divided by 1.4, right? And the change in FS and TSFC is almost nothing. It's almost the same as our original calculation, right? But here is our FS and TSFC for the turbo fan. Here it is, okay? 80% loss in specific thrust. A big loss with a high bypass ratio engine or a very low specific thrust is expected. Okay, you process a lot of air, you don't expect to get much thrust per unit of air. Does that make sense? But the improvement in TSFC over the original design is 22% decrease in TSFC. So that's good. Okay. Okay. Alrighty. I think that finishes that. Yep, we're going to do afterburning next. We're not going to do that. We're not going to do that today. How am I doing for time? Okay. I can talk about homework 6. You all see, I hope, that if you have a properly working computer program doing turbojet correctly, that it's for me, I could make it do turbofan in probably 5 minutes, maybe less. Okay, the modifications are very minimal. You all see that? Okay. Now, when I teach propulsion, once you get to having your turbofan engine computer program working, what's an interesting thing to do is to look at these 4 parameters and find some sort of optimum. And it seems like what I did in there is I had a term project where I think, remember, there are 4 parameters you need to consider, okay? And everybody had a different turbine inlet temperature. So everybody had a different one, different turbine inlet temperature assigned to them. There are 4 you've got to worry about, right? And so each student was working with 3, you know, for a fixed turbine inlet temperature. When I would see collectively everybody's paper, then I could look at the trends considering all four variables, right? And then what I would ask people to do would be successively, I'd have them look at an overall pressure ratio and then plot the trend in these things of bypass ratio versus just fan pressure ratio. And there'd always be some minimum that you'd be looking for, and that would represent the optimum design. Okay, for the turbine inlet temperature, which the student was just considering that, and for that overall pressure ratio, then the student would be required to go through a range of overall pressure ratios, finding the minimum for each one of those. So in order to find the minimum, they'd have to look at the trend of TSFC and FS for a number of calculations of fan pressure ratio and bypass ratio. Okay. See, the only two that I was really playing with here was fan pressure ratio and bypass ratio, right? That's what I was playing with. And my overall pressure ratio and turbine inlet temperature was fixed. The students' calculations would say vary 3 of those, and then when I'd see everybody's paper, then I would see the variation in turbine inlet temperature. It was, it was a little term project, I think. Okay, it's fun to play with. So, anyway, I'm not asking you to do that in here. This is, of course, in general concerns of power generation, for which gas turbine engines is a very, very important consideration, right? When I talk propulsion, that subject's roughly broken up into air-breathing propulsion systems, which is all I do in here, and rockets, which carry their own oxidizer on board. Okay, non-air-breathing systems. Okay, which I know very little about. I don't think I even did rockets, even when I taught propulsion. Okay, so anyway, we've got to look at gas turbine engines and other systems, steam power generation, and then also spark ignition engines, right? Gasoline engines. Let's look at that homework 6. A very simple assignment, assuming the turbojet is working. We're going to look at the effect on TSFC and FS as a function of bypass ratio only. Okay? So, and this is the turbofan with no mixing of hot and cold streams. So I'm going to ask you to use the same flight conditions that we've been doing, a Mach number of 0.84 and an altitude of 5 kilometers, okay? So your flight conditions are fixed, but I'm going to change your overall pressure ratio and turbine inlet temperature to these values, which is different than the values that I did for turbojet, the sample calculation, but does represent one of the points for which you're going to calculate stuff in homework 5. Okay, remember in homework 5, that's turbojet, where you're looking at the impact of overall pressure ratio and turbine inlet temperature. And you're looking at the effect on FS and TSFC. Okay, and this is one of the many values that I'm asking you to have your program cycle through. It will be one of the data points on your plot. Okay? And then we're going to set your fan pressure ratio to 2. So that means the pressure ratio of the compressor, high pressure, is going to have to be 12. It's set by OPR equal to 24 and fan pressure ratio of 2. Your high pressure compressor ratio will be 12. Use all the same isentropic efficiencies and everything that are given here in this handout. okay? No changes, okay? And what I'm gonna have you calculate is one independent variable and two dependent variables. A table of that will look like this. Bypass ratio, FS, TSFC. Bypass ratio will go from 0 to bypass ratio max. I'll talk about that in a second. In increments of 0.25. Okay? And then the plots that I'm asking you to do, since there's one independent variable and two dependent variables, one way to present it will be this. Here is FS versus bypass ratio. And this is TSFC versus bypass ratio. And you'll start from 0 and end up at some value of bypass ratio max. I'll talk about that in just a second. What trend do I expect for FS? It's going to go down, right? FS is thrust divided by m dot A, right? It's how much thrust am I producing for every unit of mass processed. I'm going to expect this thing to sort of go down like that. And that's expected. Okay? So that means for a fixed thrust requirement, you're going to have a bigger capture area for your m dot air. Okay? What do you expect for TSFC? What do you expect that to do? You're trying to improve your fuel economy. That's the whole purpose of this, right? So you want your fuel efficiency number to go down, and well, you want your efficiency to go up, and that's represented by burning less fuel, right? So this thing is going to go down like this. And I think that you should actually, when you get into a very unphysical range, it's going to pop up here, right here, okay? So it's going to be improving, and then right before it quits, okay, it goes back up, and you would never, ever actually run in this range, would you? But your calculation will give that actually will start getting worse, right at the very end. You all see that? Now, what do I mean by bypass ratio max? It's the last calculation you do where you actually get a number without it blowing up. Okay? The next calculation, okay, the one after it, 0.25 bigger than Bmax will give you a stagnation pressure that is less than your back pressure, and your computer will quit because you're going to put a little statement in there that's going to make it do something other than just blow up. Do y'all follow what I'm saying? So the last value that you compute, okay? So Bmax depends on how tiny your increments are, right? And I basically believe that if you do this thing right, you're going to find Bmax, if I remember correctly, is 4.75. That's the last calculation that you do. If I remember correctly, when you go to bypass ratio of 5, you will not be able to get a physical calculation because your stagnation pressure in your hot nozzle will be less than the back pressure. Okay, and if you try to calculate that, square root of a negative temperature, you know, blow up, computer program blows up. I've had students that were curious to look at what the, you know, a better value of Bmax would be, because the stagnation pressure at 5 is just a little bit lower than the back pressure. So I've had students out of curiosity do the increment, instead of increments of 0.25, they'll change it to like 0.1 or 0.01. And I think it's like, I think really when you do that, I think like Bmax is like 4.98 or something like that. So, you know, but for you all, I believe it's 4.75. Okay? So this is what you do. You do these calculations, do those plots, and make sure you give me a table so that I can spot check your numbers to 58 decimal points. Okay? It has to be right to 58. Okay? So that I know you did it right. Okay? So you need a computer for the 26th century that will give you that precision, right? Any questions about that? Isn't this fabulous? And I guess I need to go home and think about a due date for it, right? Does anybody here have submissions for homework 3 or retry? If so, please give them to me, and I will correct them and give them back to you next time.